Hi guys, today we have our lecture 4 of module 3 quantum mechanics. In this session, I am discussing about applications of Schrödinger wave equations. So, applications of Schrödinger wave equations, there are two applications, particularly named one-dimensional infinite square well potential and quantum mechanical tunneling. So, our first topic is infinite square well potential. We know that in atoms, electrons are restricted to move around nucleus in a fixed orbit. They are bound to the parent nucleus. The behavior of such bound electrons can be described by particles in a potential well. For simplicity, we consider the motion in a one-dimensional potential well. Consider a particle of mass m confined in a one-dimensional potential box of infinite depth and a finite width small a, moving in the x direction. In order to ensure that the particles remains in the box, we shall assume some boundary conditions that v is equal to 0 everywhere within the box and v is equal to infinity outside the box. That is, the potential v of x is equal to 0 where 0 less than or equal to x less than or equal to a, and infinity x less than 0 and x greater than 0. Here we have the one-dimensional Schrödinger wave equation for the single particle is minus h cut square by 2m dou square psi by dou x square plus 2m by h cut square into e minus v is equal to psi, which equal e minus v into psi is equal to 0, which is our Schrödinger equation. So if v is equal to 0 inside the box, that means dou square psi by dx square plus 2me by h cut square psi is equal to 0, and let k square is equal to 2me by h cut square, that is dou square psi by dx square plus k square psi is equal to 0. The solution for this equation, psi of x can be written as a sin kx plus b cos kx. From the boundary condition, if we are applying the boundary condition in this equation, at x is equal to 0, psi of x is equal to 0, and x is equal to L, psi of x is equal to 0. And x is equal to 0, at x is equal to 0, psi of x is equal to 0. So if we are substituting this, then this will become 0 is equal to a sin k into 0 plus b cos k into 0. So instead of x, we put substitute 0. Then we will get b is equal to 0. That is, psi of x is equal to a sin kx. And then second condition, at x is equal to a, psi of x is equal to 0. So this will become 0 is equal to a sin k a. So instead of x, we substitute x is equal to a. So ka is equal to n pi, or k is equal to n pi by a. So the equation will become psi of x is equal to a sin n pi by a into x. So here we need to find the value of a. So in order to find a, apply the boundary conditions to this. So we have minus infinity to infinity modulus of minus infinity to infinity psi star dx is equal to 1, or here 0 to infinity, 0 to a psi star dx is equal to 1. That is 0 to a sine n pi by ax into a sine n pi by ax pi by a into x is equal to 1. ഇതിനെ നമ്മൾ സ്പ്ലിറ്റ് ചെയ്ത് എഴുതി, സൈയും സൈ സ്റ്റാറും ആണ്, അത് രണ്ടായിട്ട് സ്പ്ലിറ്റ് ചെയ്ത് എഴുതി. സോ എ സ്ക്വയർ കോമൺ ആയിട്ടുണ്ട്. സോ എ സ്ക്വയർ ഇൻറ്റു ഇൻ്റഗ്രൽ 0 to a സൈൻ സ്ക്വയർ n pi by a x is equal to 1. So what is sine square a? 1 minus cos 2a by 1 minus cos 2 by 1 minus cos 2x by 2. So here a square into integral 0 to a 1 minus cos 2 n pi by a into x divided by 2 dx which is equal to 1. So ഇതിനെ സ്പ്ലിറ്റ് ചെയ്യുന്ന സമയത്ത് എ സ്ക്വയർ ഇൻറ്റു ഇൻ്റഗ്രൽ 0 to a 1/2 dx minus a square by 2 integral 0 to a cos 2 n pi by a x dx is equal to 1. So from this term will be 0 because cos 2 n pi by integral 0 to a cos 2 n pi by a x dx is equal to 0 ആണ്. So the equation will become a square into integral 0 to a 1/2 dx is equal to 1, or a square by 2 is into small a is equal to 1, or a is equal to root of 2 by a. So the wave function of particle in a potential box of length a will be given as psi of x is equal to a sine n pi x by a, and here we have value for a, so substitute the value for a in this equation. So we will get psi of x is equal to root of 2 by a sine n pi x by a, which is the wave function of particle in a potential box of length a. This figure shows the wave functions of a particle confined to a box with rigid walls. Here psi 1, psi 2, psi 3 are the wave functions of the particle inside the box. Next is energy eigenvalues. We need to find the energy eigenvalues. So here we have Ka is equal to n pi, or we have k square is equal to 2me by h cut square. So we can equate these two. N square pi square is equal to 2me by h cut square, or En is equal to n square pi square h cut square by 2ma square, or En is equal to n square h square by 8ma square. So the different values of energy for n are called energy eigenvalues, and the psi n of x is equal to root of 2 by a sine n pi x by a is eigenfunction. So eigenvalues and eigenfunctions. Second application is quantum mechanical tunneling. According to classical mechanics, when a particle of kinetic energy E approaches a potential barrier V0, it bounces off without entering the other side. But in quantum mechanics, the wave functions representing the particle wave does not vanish on the other side of the barrier. This shows a finite probability of the particle penetrating to the barrier. The phenomenon of penetration of particles through barriers higher than their own incident energy is known as tunneling. So here we consider a beam of identical particle of kinetic energy E. Let the beam be incident from the left side on the potential barrier of height V0 and a width A. On either side of the barrier V is equal to 0. That means the potential is 0, that is no forces acting on the particles there. The potential can be represented as V is equal to 0 for x less than 0, where x less than 0 means the region 1. This is x less than 0. And V is equal to V0 for x less than 0 less than x less than L, which means here inside this portion. And V is equal to 0 for x greater than L, that is region 3. Let psi1, psi2 and psi3 be the wave functions in the regions 1, 2 and 3 respectively. So this case only we will get E minus V10. So in this first case, the Schrödinger wave equation dou square psi 1 by dou x square plus 2m by h cut square into E psi 1 is equal to 0. And second case, dou square psi by psi 2 by dou x square plus 2m by h cut square into E minus V into psi 2 is equal to 0. Then third region, dou square psi cube by dou x square plus 2m by h cut square E psi 3 is equal to 0. These are the three Schrödinger equations of the particles in these three regions, or in these regions, region 1, region 2 and region 3. Because of the wave nature of the material particle, they are tunneling through the barrier. This phenomenon is known as a barrier penetration or a quantum mechanical tunneling. And for a wave functions of the particle of energy E less than V0, the three different states is shown here. So this is a chapter. Thank you.